Hello everyone, welcome to the fifth lecture of this third week on we are discussing principle of sensing, and this is a course Microsensors and Nanosensors. We have discussed four different principles including capacitive, inductive, resistive and piezoelectric. In the series, today we are going to discuss pyroelectric devices or pyroelectric sensors. But before we understand a pyroelectric sensor, let us understand pyroelectric material first. Okay. Of course, this is very much related to piezoelectric. So, let us understand a pyroelectric material. A pyroelectric material are crystalline substances which can generate electrical charge when exposed to heat flow. Please note the word heat flow because this is very important and sometimes this is confused with temperature. We are not interested in measuring temperature here. These materials can detect a change in temperature, or because of this change in temperature there will be a heat flow, so it can detect that. It cannot measure absolute temperature. Okay. As I have mentioned that these pyroelectric materials are very closely related to piezoelectric material. After a few slides we will talk about how they are related to each other. Okay. Similar to the piezoelectric devices that you have seen, where I have a piezoelectric thin film or thin layer, and on top and bottom I have two electrodes so that it constitute a kind of capacitor. Similarly, a pyroelectric sensor has two electrodes at the opposite side of the crystal. Again, it depends that how you want your sensor to work. Similar to what we have seen in piezoelectric devices. We have seen that if I make a single electrode, I will be able to measure force at that particular point. However, better to pattern it to measure force in a large area and so on. Okay. So, pyroelectric sensor is also a capacitive device, okay, because you are sandwiching this pyroelectric material between two different electrodes. So, however, this capacitor can be electrically charged by flux of heat. Okay. If you have a heat flow or you have a heat flux, you can charge this capacitor. Okay. The detector does not require any external electric bias. Okay. Therefore, it is a direct converter of heat into electricity. Okay. Since a change in temperature basically require a propagation of heat, a pyroelectric device is a heat flow detector and not the heat detector. Okay. So, heat is caused by temperature. So, as I have mentioned earlier also that it cannot measure absolute temperature. Similarly, it cannot measure the heat. It can measure the flow of heat. Okay. And that is reflected in the equation of current for a pyroelectric device. Okay. Usually, the current is given by A into P into d theta by dt, where A is the cross sectional area of the device. This P is the pyroelectric coefficient, while this d theta and dt is the heat flow or change in the temperature. A pyroelectric material considered as a composition of large number of minute crystallites which are randomly oriented, with each behaving as a small electric dipole. Okay. So, you can consider it as a bigger grain of small dipoles which are randomly oriented. Okay. So, what happened that above certain temperature, which is known as Curie temperature, the crystallites have actually no dipole moment. You might be knowing about Curie temperature. It has to do with ferroelectricity, right. So, the Curie point temperature or simply Curie point is the temperature at which a ferromagnetic material actually loses its magnetic properties and it becomes a paramagnetic material. Okay. So, what happened in a pyroelectric material, which is nothing but a crystallite of small electric dipoles oriented in different direction, above this Curie temperature, the crystallite will have no dipole moment. Okay. However, similar to the polling that we have done in piezoelectric material, if you remember, I discussed that you have a naturally existing piezoelectric material like quartz. At the same time, you have a synthetically manufactured piezoelectric material like barium titanate and PVDF. Okay. However, in their existing form, these two materials, say PVDF and barium titanate, they do not have a piezoelectric material, and we have to do manual polling. Okay. Similar to polling, in this case of piezoelectric material, we call it manufacturing. So, if you do this manufacturing, then only your material will behave as a pyroelectric material, okay, or it will start showing pyroelectric properties. Okay. There are various mechanisms which is behind this pyroelectric behavior. Basically, there are two popular pyroelectricity mechanism. One is primary pyroelectricity and the second one is secondary pyroelectricity. Let us try to understand both of them because they are very crucial. Particularly, we will focus on secondary pyroelectricity because that is the basis of several sensing devices. Okay. So, pyroelectricity, primary pyroelectricity is simple device where temperature changes or heat flow causes shortening or elongation of individual dipole. Okay. So, because of this heat flow or upset in temperature, there is shortening, either shortening or sometime elongation of this individual dipoles that we have just seen. Okay. It affects the randomness of the dipole orientation and therefore, pyroelectricity is generated or it starts showing pyroelectric behavior. Okay. And that is why since it is direct conversion of this temperature flow or heat flow to pyroelectricity, I call it primary pyroelectricity. Okay. At the same time, there is another phenomena which is known as secondary pyroelectricity exists. Okay. So, this secondary pyroelectricity is described as a result of this piezoelectric effect, that is a development of strain in the material due to thermal expansion. Okay. So, we will see that how a thermal expansion, which is of course related to piezoelectricity, can in turn give you a pyroelectric behavior. Okay. However, when you do not have a direct conversion of this heat flow to affect this dipole moments. Okay. I call it secondary pyroelectricity. Okay. So, if I brief it, if there is a direct conversion of temperature flow or heat flow to a change in dipole moments, I will call it primary pyroelectricity. However, if there is no such change, however, in turn it is coming from some external mechanical forces or external mechanical deformation, okay, and which is important in piezoelectric effect or in piezoelectric material, I have a thermal expansion which I can relate with pyroelectricity. We will see in brief what is secondary pyroelectricity in detail. Okay. So, I have a pyroelectric material, just have a look on this. I have a pyroelectric material and two electrodes on both the side, and the top layer I have painted it with some polymer or some, I have this gold black kind of structure which can absorb heat. Okay. So, of course, this heat is coming in the form of infrared radiation. Usually, these pyroelectric devices are useful for infrared detection, particularly in the range of 2 micrometer to 14 micrometer. Okay. Let us assume that heat is applied to the top of the sensor in the form of infrared radiation. Okay. This heat absorbing layer absorbs radiation and warms up the upper side of the material. So, this layer is now getting heated by the external flow of flux of this infrared. Okay. As a result, the top side of the material is expanding, okay, or it starts showing some mechanical deformation. Okay. The expansion leads to flexing of the sensor, which produces stress and change in the dipole orientation. Because of this expansion of this top layer, there is a mechanical stress which is induced in this plate which is just beneath this heat absorbing layer, and because of this stress there is a change in dipole orientation. Okay. So, since it is also a piezoelectric material, the stressed material generates electric charges of the opposite polarity on the electrode. Okay. And therefore, a voltage is observed across the electrodes. Okay. So, if you see in this case there is not a direct heat flow, but what I have done is this orientation of these dipoles has changed because of mechanical deformation. Of course, the cause of that mechanical deformation is not a mechanical force, but some light absorption or say some light bombarding on the top of this electrode. Okay. So, if I brief this sequence that how this pyroelectricity is generated, I can say that the first step is there is some thermal radiation falling on the top of the structure. Okay. Then this top of structure is absorbing some heat. So, the first step is thermal radiation, second is heat absorption, and third is thermally induced stress. Okay. There is a expansion of the top layer. Because of this thermal expansion there is a induced stress in that, and when there is a induced stress there is a change in dipole orientation. Okay, and because of that there is a electric charge generated, and in turn you get voltage. So, the sequence is thermal radiation, heat absorption, thermal induced stress and electric charge generation, and of course, at the last voltage generation, right. That is the ultimate aim. So, if you have a change in voltage, you can quantify it against some external stimuli, maybe some change in temperature or heat flow. Okay. Let us try to quantify this charge first. Okay, and then we will try to comment on the voltage. Okay. If M is the capital M is the dipole moment, so the dipole moment of a bulk pyroelectric sensor can be given as this dipole moment M is equal to mu into A into H, right. So, where mu is the dipole moment per unit volume of this material, and A is the cross sectional area, and H is the thickness of the sensor, right. So, this is my dipole moment. A charge Q can be picked up by these electrodes which develops a dipole moment. I am talking about this particular figure. Okay. So, I have this dipole moment in the form of mu into A into H. Okay. And the charge can be picked up by the electrodes, the top electrodes which develops the dipole moment across the material. So, M naught can be given as QA into H, where again H is the thickness of the material. However, this M naught should be equal to M. Therefore, QA should be equal to mu into A, because if I compare this equation, QAH is equal to mu A into H, right. So, your QA is equal to mu into A. Okay. Let us call this as first equation and this is as second equation. Okay. We know two different things, particularly about the behavior of a dipole moment. Okay. The dipole moment varies with temperature, because of which a charge is induced. Okay. And second thing is the thermal absorption can also be related to dipole change. So, two things are there. Dipole moment varies with temperature and thermal absorption can be related to dipole change. Okay. Therefore, this mu must be considered as a function of temperature as well as heat flow. Okay. So, mu is a function of a temperature Ta and incremental thermal energy del W, okay, which is basically absorbed by the material. So, change in the charge is equal to A into mu, which I have this second equation is showing Q is equal to mu into A, or del Q can be written as A into mu, where this mu is a function of Ta and dW that we have just seen. Okay. So, this charge is very important and this is what we intend to detect in the sensors that we are going to discuss in next modules. Okay. Now, let us see its equivalent circuit, because equivalent circuit of this particular device is very crucial in developing the interface circuits. Okay. So, a pyroelectric sensor is connected to a resistor, say RB, which is shown over here. Okay. This resistance represent either the internal leakage resistance or a combined input resistance of the interface circuit which is connected to the circuit. Okay. So, if you have a pyroelectric sensor, you can understand this connected to a circuit RB. In the circuit RB, this resistance represent the internal leakage resistance. Okay. And if I have to draw its equivalent circuit, I have to draw it like this. You have I, C and RB, where the current source which generates a heat induced current I is shown over here. Okay. Capacitor of the sensor is C and the leakage resistance is RB. Okay. So, this is a equivalent circuit for a pyroelectric sensor. Okay. Now, depending on the application, the output signal of the sensor can be taken either as current or as a voltage, and that is the biggest advantage in case of pyroelectric sensors. So, you do not have to worry much about the input behavior of the internal circuit that or interface circuit that you are going to discuss, because it can take both current as well as voltage depending on how you are connecting it and what is your interface circuit. Okay. So, if you see this diagram, you have simply a current source, of course, which is dependent on heat and other things. Okay. And you have a capacitor and RB in parallel. Okay. So, being a capacitor, the pyroelectric devices is discharged when connected to a resistor RB. Okay. The current and voltage across the resistor represent the heat flow by the induced charge. Okay. Now, these pyroelectric devices can be characterized by two different coefficients. One is pyroelectric charge coefficient and second is pyroelectric voltage coefficient. Okay. So, a typical pyroelectric coefficient is represented by P subscript Q, while pyroelectric voltage is represented as P subscript V. Okay. And this PQ is given as dP by dt, where T is the temperature and P is or PS is the spontaneous polarization. This PV, the voltage coefficient, is given as dE by dt, where E is the electric field strength. So, basically it is nothing but pyroelectric charge coefficient you can understand as the slope of a temperature and polarization curve, while pyroelectric voltage is electric field and temperature curve. Okay. The slope of electric field and temperature curve. Okay. Both coefficients are related by the electric permittivity epsilon r and dielectric constant epsilon naught. Okay. So, if you divide this PQ by PV, basically you get del PS by del E, or differentiation of polarization with respect to the electric field strength. Okay. And this is nothing but epsilon r into epsilon naught, right. The polarization is temperature dependent, we all know. Okay. Both pyroelectric coefficients are also a function of temperature that we have just seen. Okay. If a pyroelectric material is exposed to a heat source, its temperature increases, say, by del T, the corresponding charge and voltage change can be described as del Q is equal to PQ into A into del T, okay, where del T is the change in temperature and A is the area. PQ we have just seen is the pyroelectric charge coefficient. Okay. Similarly, del V can be given as PV into H into del T, where PV is the pyroelectric voltage coefficient. Okay. Again, these two equations are very crucial in designing a sensor, because ultimately what you are going to measure is the change in this charge or change in this potential. Okay. Remembering that the sensor's capacitance can be defined as del Q by del V or epsilon R into epsilon naught into A by H. Okay. From this equation, I can say that this del V is equal to del Q by C. Okay. Del V by equal to del Q by CE. Okay. Now, del V can be found by putting these values in this equation, and finally what I get is del V is equal to P into A by CE into del T, or this in turn is equal to PQ into epsilon R epsilon naught by H into del T. Okay. So, if you see this change in voltage, okay, or the peak output voltage is basically proportional to the sensor's temperature rise, or del T, proportional to pyroelectric charge coefficient, this PQ, and inversely proportional to its thickness. Okay. And these 3 points are very important when designing a pyroelectric sensor. Okay. Because this equation gives you the peak output voltage that you obtain from a pyroelectric sensor. Okay. I hope that this pyroelectric material and behavior is clear to you. Okay. Now, a crystal is considered to be pyroelectric if it exhibits a spontaneous temperature dependent polarization. I can say like that, right? A crystal is considered to be pyroelectric if it exhibits a spontaneous temperature dependent polarization. Okay. Of the 32 crystal class that exist, 21 classes are non-centrosymmetric and 10 of these exhibit actually the pyroelectric properties, and all of them exhibit also piezoelectric property. Okay. So, in addition to pyroelectric properties, all these materials exhibit some degree of piezoelectric properties as well. Okay. So, we know that when the pyroelectric sensor is subjected to a thermal gradient, its polarization varies with the temperature of the crystal, right. So, this is a typical curve of polarization versus temperature and pyroelectric coefficient versus temperature. Just have a look on this graphs. Okay. The voltage pyroelectric coefficient PV basically is a slope of this curve. Okay. It increases dramatically near the Curie temperature. This point is Curie temperature, okay, at which the polarization actually disappears and material permanently loses its pyroelectric properties. Okay. The curve implies that the sensor sensitivity increases with temperature when it while at the same time it also introduces some non-linearity in the device. Okay. So, with this I am sure that the phenomena of pyroelectricity is clear to you. Pyroelectric phenomena is very crucial, particularly for devices which uses infrared emitters. Okay. Mostly you will find that this infrared emitters or infrared based systems are very important in case of occupancy sensors. Okay. Like if a person, if I want to detect that if a person has entered into class at 10 AM sharp or not, okay, or say if I want to monitor that if that particular person is existing in that classroom or not, okay, I can simply employ infrared sensor. Of course, when you need infrared for a sensor, you need an infrared source and you need a detector. Okay, because what you want to detect is this infrared. Okay, for the case of this say human being, our body itself can act as a infrared source. Okay, or say far infrared or mid infrared, depending on what object I am talking about. Okay, and then you have a pyroelectric materials or pyroelectric sensors placed nearby to detect or to capture this infrared radiation. Okay, and accordingly I have shown you the secondary pyroelectricity, that the top area absorb this infrared. Okay, and at the same time it bends, it deform. Okay, and because of that there is a disruption in the dipole moment which is existing there. Okay, and we by some mean we detect that, and accordingly we calibrate that something has been detected. Okay. So, that is all about our pyroelectricity. In the previous classes, as I have mentioned, we have discussed this capacitive devices, inductive devices, resistive devices. We have seen geometry factor for all of them. Okay. For example, For a parallel plate capacitor, we have seen that A by D is a geometry factor. Okay, we have also seen other configuration of this sensors, like say coaxial conductor kind of structure, or for inductor also we have seen several iterations. Okay, and piezoelectric devices we have seen extensively, that how it can be used for pressure and strain detection. And finally, today we have covered the pyroelectricity or pyroelectric behavior. Okay, in the next class we will be discussing interface circuit. Okay, if you see this structure, you have a sensor in place. You have after this sensor you have a analog interfacing circuit. Okay, the input of this ADC is the output of this analog interface circuit. Okay, and this ADC output is given to this microcontroller. Okay, and then you have a communication interface at which this communication medium exists. Okay, and of course you have power supply and other things in place for detection of these things. Till now what we have discussed is these sensors. Okay, in the next class we will also see little bit on interfacing circuits, and if time permits little bit on ADCs. Okay, and if we have this understanding, I think we are ready to take challenges in this particular area. Okay, so you may have separate courses on sensor signal conditioning or sensor interface circuit, but in this course also we will try to devote around 5 lectures to this interface circuit. Okay, so we will meet in next class with interface circuit discussion, including some excitation circuits to power up this sensor. Thank you.